Osiris-Rex is NASA's first asteroid sample return mission. Launched in 2016, rendezvoused with asteroid Bennu in 2018, collected a sample from the surface of the asteroid in 2020, and then brought it back to Earth where it landed in Utah.
For billions of years, the origin of life on Earth has been one of science's greatest mysteries. Now, a tiny asteroid may have finally provided a clue. NASA's recent analysis of samples returned from this space rock reveals sugars, amino acids, and other molecules essential for life. Could these cosmic ingredients be the missing pieces that explain how life first sparked on our planet? Stay with us to know the surprising details. How Osiris-Rex brought Bennu home. The story of Osiris-Rex began in 2016 when NASA launched a spacecraft on a mission unlike anything it had attempted before. The goal was clear: travel across millions of miles of empty space, reach a small ancient asteroid named Bennu, collect a handful of its rocky surface, and bring it safely back home. The spacecraft began its long journey from Earth and spent 2 years traveling before it finally arrived near Bennu in 2018. Bennu was a small, round-shaped asteroid that floated quietly in the dark. Osiris-Rex slowly moved in, studied the surface from every angle, and prepared for the moment scientists had planned for years. In 2020, the spacecraft extended a long sampling arm that worked like a gentle vacuum. It touched the asteroid for only a few seconds and captured loose dust and stones. With the sample secured inside a sealed capsule, the spacecraft pulled away. By the time it turned back toward Earth, it had traveled almost 4 billion miles. Returning the sample was another enormous challenge. The capsule had to survive the fall through Earth's atmosphere, land safely, and stay untouched by anything on our planet. In September 2023, Osiris-Rex flew past Earth and released the capsule from more than 60,000 miles away. 4 hours later, it dropped into the Utah desert. When the parachute opened higher than expected, teams held their breath, unsure of what would happen. Moments later, the landing was confirmed. The small container was found in perfect condition, unbroken and tightly sealed. Within 2 hours, recovery teams carried it to a temporary clean room at the Utah Test and Training Range. Every step from that moment was slow and carefully controlled. The sample had to remain pure, untouched by Earth's moisture, soil, or air. It was soon transported to the Johnson Space Center in Houston and placed inside a nitrogen-filled laboratory. Scientists entered the room in protective suits and opened the capsule layer by layer. Inside, they found about 120 grams of dark, rich material. It was a mixture of minerals, tiny grains, clay, and dust that had remained unchanged for more than 4 billion years. Researchers believe it is some of the most pristine asteroid matter ever brought to Earth. Unlike meteorites that crash through the atmosphere and become contaminated, this sample arrived fresh and preserved. It offers scientists a chance to study what the early solar system might have looked like in its first moments. The true mystery now begins, because within this small collection of ancient dust may lie clues that could change everything we think we know about how life first began. Unique cosmic ingredients. When scientists began examining the tiny grains from Bennu, they quickly realized they were looking at something extraordinary. Inside the sample, they found a rare magnesium-sodium phosphate mineral. This discovery was surprising because such minerals usually form in the presence of liquid water. It suggested that Bennu was once part of a much larger parent body, one that may have contained oceans or long-stored reservoirs of water. In other words, Bennu's ancient home might have been a small, wet world drifting through the early solar system. Members of the mission team were stunned. Dante Lauretta, the principal investigator of Osiris-Rex, described the material as a large, pristine asteroid sample that was rich in nitrogen and carbon and came from what he called a formerly wet world. To him and many others, the sample was not just dust. It was a message from a place that once supported chemical activity in water, a setting where interesting reactions could have unfolded. As scientists reviewed the mineral content, they identified 11 different types that often appear when salty water slowly evaporates. These included minerals such as calcite, halite, and sylvite. Their presence showed that Bennu's parent body once held water that carried dissolved salts. Over long periods, that water must have either cooled or disappeared, leaving behind the solid crystals. Similar types of salty brines have been detected or suspected on places like the dwarf planet Ceres and the icy moon Enceladus, which hint that such environments may be common in the solar system. The implications reached far beyond Bennu itself. Inside the sample were the same chemical building blocks that create amino acids, which help form proteins. There were also nucleobases and phosphates, which are the foundation of genetic materials. These findings strengthened a powerful idea. The ingredients for life may not have been invented on Earth. They may have already existed across space long before our planet formed. Asteroids like Bennu could have delivered these ingredients to the young Earth through gentle impacts, providing the first spark for biological chemistry. The picture that now emerges is both simple and astonishing. Across the darkness of space, tiny worlds were carrying the seeds of life within their dust and minerals. Some of those seeds eventually reached Earth and helped shape the world we know today. Yet even with all these clues, one essential piece is still missing. It is a piece that could make or break the possibility of life's cosmic origin. Sweet surprise with the discovery of sugars. In early December 2025, researchers have made one of the most remarkable breakthroughs yet. A team led by Yoshihiro Furukawa from Tohoku University in Japan discovered sugars inside the powdered material returned from the asteroid. These findings, published in Nature Geoscience, revealed ribose, the 5-carbon sugar that forms the backbone of RNA, and for the first time ever in an extraterrestrial sample, glucose, the 6-carbon sugar that fuels so many life forms on Earth. Scientists emphasized that these sugars did not mean life once lived on Bennu, but they showed that the building blocks of biology were spread widely throughout the early solar system. For life on Earth, sugars like ribose and deoxyribose are essential. Ribose supports the structure of RNA by forming the sugar phosphate backbone that holds information carrying nucleobases. DNA carries genetic instructions, and RNA performs vital tasks that no known life can function without. To find ribose already formed inside this ancient asteroid material suggested that chemistry leading toward life was happening long before Earth became a habitable world. Furukawa's team carefully extracted these delicate molecules from about 600 milligrams of powdered Bennu dust. The sample was soaked in water and acid, allowing molecules to separate. Then, through sensitive techniques like chromatography and spectroscopy, scientists detected chemical fingerprints that matched ribose and glucose. NASA scientists noted that with sugars, nucleobases, phosphates, and amino acids all identified, the inventory of ingredients crucial to life was essentially complete within Bennu itself. This finding also added powerful support for the RNA world hypothesis, a major idea in astrobiology which suggests that early life may have begun with RNA rather than DNA. In a companion study published in Nature Astronomy, scientists reported the detection of 14 of the 20 amino acids used by life on Earth. They also found all 5 nucleobases that Earth life uses to store and transmit genetic information. These discoveries were joined by the detection of high levels of ammonia and formaldehyde. Under the right conditions, ammonia reacts with formaldehyde to form amino acids, which then join together into long chains that create proteins. Proteins drive nearly every biological function known today. Although similar molecules have been found in meteorites before, the Bennu sample offered something those meteorites never could. It was pristine and untouched by Earth's atmosphere. Danny Glavin, a senior sample scientist at NASA's Goddard Space Flight Center, said these clues were so tiny and so fragile that only a sample returned directly from space, handled with meticulous care, made these discoveries possible. Other teams focused on the environment where these molecules might have formed. Scientists led by Tim McCoy at the Smithsonian and Sarah Russell at the Natural History Museum in London described an ancient setting that could have encouraged the chemistry of life, a world with water, salts, and the right ingredients mixing in slowly evolving reactions. With sugar now in the mix, the ingredients for life are nearly complete. Yet even with everything in place, the leap from chemistry to life still felt impossibly large. And then came a discovery that pushed the mystery even deeper, opening a door no one expected. The unexpected polymer that could bridge molecules and life. A team led by Scott Sanford at NASA's Ames Research Center and Zach Gainsforth at UC Berkeley uncovered a gum-like nitrogen and oxygen-rich polymeric substance within the asteroid dust. It had never been seen before in any meteorite or sample from space. Researchers began calling it space gum or space plastic. It likely formed during the earliest days of the solar system, when Bennu's parent body began to warm and transform. This material was once soft and flexible, but after billions of years in cold space, it hardened. At its core, it contained complex polymer-like structures packed with nitrogen and oxygen. Such molecules could have played an important role in early chemistry by helping simple building blocks concentrate and interact. To the scientists studying the origins of life, this substance became a possible missing link, a medium that may have helped bridge the gap between scattered molecules and more organized prebiotic reactions. Bennu's parent asteroid formed inside the swirling solar nebula that gave birth to the planets. It carried minerals, ices, and gases from that ancient cloud. As it slowly warmed through natural radiation, ammonia and carbon dioxide reacted to form carbamate. Carbamate is water-soluble, but before Bennu became a watery world, the compound had enough time to polymerize. It linked with itself and other molecules, creating chains strong enough to survive later flooding. This meant the strange gum-like substance formed early, before liquid water spread through the asteroid's interior. Sanford described this material as one of the earliest chemical alterations preserved inside Bennu. Gainsforth remembered the moment they realized how unusual the sample was. When the first images appeared on the monitor, the entire team fell silent. It was something entirely new, and understanding it took months of experiments and careful analysis. Studying the material required delicate work. Using an infrared microscope, the team selected unusual carbon-rich grains. At the molecular foundry in Berkeley, they reinforced each tiny particle with a platinum layer. They welded a tungsten microneedle onto it, lifted it, and shaved it to an ultra-thin sheet with a beam of charged particles. Once a grain was 1,000 times thinner than a human hair, they analyzed its chemistry using electron microscopy and high-resolution X-ray spectroscopy at the Advanced Light Source. These tools revealed the material's strange signature and its hodgepodge structure that varied from grain to grain. Scientists noticed the polymer had once been pliable, bending under slight pressure like used gum or soft plastic. It was translucent and became brittle under radiation, similar to a weather-worn lawn chair. Sanford compared its chemical groups to polyurethane on Earth, though the asteroid version was far more chaotic. It was not a neat polymer, but a tangled ancient mix of bonds created long before Earth formed. Researchers think this space gum may have helped early chemical building blocks stick together, gather in one place, and react. It adds a new possibility to how life's chemistry may have begun, not only on Earth but across the young solar system. And yet, as scientists studied this strange cosmic glue, they began noticing something else buried even deeper in the samples. Something older than Bennu. Something born in the heart of long-dead stars. Discovery of pre-solar material. The deeper scientists looked into Bennu, the further back in time the asteroid seemed to reach. In a detailed analysis led by Ann Nguyen at NASA's Johnson Space Center and Tom Zager at the University of Arizona, scientists identified tiny grains that predated the birth of our solar system. These fragments, known as pre-solar grains, are literal stardust from long-dead stars. A paper in Nature Astronomy confirmed the finding. Nguyen's team examined pre-solar grains trapped inside 2 different types of Bennu rock. Their results stunned the scientific community. The samples contained 6 times more supernova dust than any other space material ever studied. This meant Bennu's parent body formed in a region of the early solar disk enriched with debris from dying stars, a part of the nebula where cosmic chaos was still shaping worlds. Even more surprising was what survived. Bennu's parent asteroid had once been heavily altered by water, a process that usually destroys fragile pre-solar material. Yet pockets of untouched stardust and primitive organics were still preserved inside the sample. Nguyen noted that these fragments held more organic matter and delicate pre-solar silicates than scientists expected, proof that some early materials escaped the sweeping wave of alteration. They were like tiny time capsules, untouched since the dawn of the sun. Each grain carried its own origin story. Some formed in blistering temperatures close to newborn stars. Others developed in icy, interstellar-like regions far from any heat. Together, they showed that Bennu's ancestor wasn't born from one place, but from many, a gathering point where materials from across the galaxy merged into one body. It suggested that the ingredients that later seeded Earth may have had a truly cosmic lineage, shaped by the birth and death of stars scattered across the Milky Way. Behind this enormous effort stood the Osiris-Rex team, Dante Loretta guiding the mission's scientific heart, Lockheed Martin building and operating the craft, NASA Goddard managing systems and safety, KNETX navigating across millions of miles, and international collaborators like the Canadian Space Agency and JAXA contributing crucial instruments and science. Their careful planning and precision made it possible for a sample untouched by Earth to reveal these ancient clues. The discovery of pre-solar grains changed the scale of the story. Life's ingredients didn't just come from asteroids or comets. They came from stars older than our Sun, carried across space, gathered into Bennu, and eventually delivered to Earth. And if these cosmic seeds were scattered here, they may have been scattered elsewhere too, across moons, planets, and worlds still waiting to be studied. Now, the final question turns toward delivery, how these ancient materials actually arrived on Earth, and what that might mean for life beyond our planet. Could asteroids have seeded early Earth? Long before Earth calmed into oceans and continents, the young planet was a violent battlefield. For millions of years, giant rocks, icy fragments, and carbon-rich asteroids rained down from space in what scientists call the heavy bombardment era. Each collision shook the newborn world, sending shockwaves through oceans of magma and clouds of steam. But hidden inside some of these incoming objects were precious gifts, the chemistry that life would one day depend on. Asteroids like Bennu, or older fragments that once belonged to its ancient parent body, may have been part of that cosmic delivery system. Scientists believe these space rocks, loaded with water-bearing minerals and organic molecules, slammed into early Earth and transferred their fragile cargo into our oceans, atmosphere, and soil. These impacts did not merely scar the planet, they may have enriched it. Even if Earth got seeded, the leap from raw molecules to living systems remains enormous. But maybe the missing piece lies in how these molecules assembled. which leads us to the origin of replicators. A new debate about life on Earth. The Bennu findings have ignited a wave of fresh ideas about the role asteroids may have played in shaping the chemistry of life. Some researchers suggest that beyond delivering simple molecules, asteroids could have carried chemical systems already partially organized, capable of interacting and evolving under the right conditions. This implies that prebiotic chemistry was not restricted to Earth, but may have been an active process in space, shaped by radiation, temperature variations, and the internal dynamics of asteroid parent bodies. Planetary scientists are exploring the notion that primitive asteroids like Bennu were not uniform but chemically diverse, containing microscopic regions where complex reactions could take place. The combination of organics with minerals and traces of ancient water may have created microenvironments akin to natural laboratories. This has prompted some experts to describe Bennu and similar asteroids as prebiotic reactors operating on geological timescales. Another intriguing idea comes from cosmochemists who are investigating how stellar materials influence the formation of these asteroids. Pre-solar grains embedded within Bennu indicate that the asteroid incorporated dust from multiple generations of stars, suggesting that prebiotic chemistry may have inherited a cosmic blueprint. These grains could have catalyzed reactions or acted as scaffolds for the assembly of larger organic structures. The presence of diverse chemical environments within a single asteroid challenges traditional models of life's origin being a purely Earth-bound phenomenon. Astrobiologists are also re-evaluating the timeline for life's emergence. If asteroids supplied not only ingredients but partially organized molecular networks, life on Earth may have begun sooner than previously assumed. Some researchers argue that prebiotic chemistry delivered from space could have accelerated the formation of self-replicating molecules by offering already concentrated and chemically compatible compounds. The Bennu discoveries are reshaping the scientific narrative, moving the discussion from Earth-centered chemistry to a solar system-wide perspective. They encourage consideration of how chemical evolution might operate on small bodies throughout space, hinting at the possibility that life's potential may have been sown far beyond our planet. These insights open a new frontier for astrobiology, one that examines life's beginnings not as a single event, but as a chemical process distributed across the cosmos. What do you think about the idea that asteroids like Bennu could have seeded life on Earth? Share your thoughts and theories in the comments below.